It has been 7 days since Perihelion, November the 5th, 2025. Across multiple observatories, 3i Atlas is no longer behaving like a normal interstellar traveller. The data pouring in since October 29th show a sudden flare, a violent brightening no one predicted. Its magnitude rose faster than any thermal model could justify, and for a brief window, instruments tracking near the Sun registered a structured pulse of light, rather than a random outburst. Teams at ESA and NASA moved quickly, activating emergency observation modes. Solar coronagraphs showed a stretched halo forming around the object, thin, almost transparent, yet stable enough to persist for hours. What should have been a simple increase in dust reflection instead looked organised, layered, as though something within 3i Atlas had ruptured from pressure or design. Spectrographs confirmed emissions of carbon dimer, ammonia, and hydroxyl bands without the expected dust tail. That absence is what alarmed scientists most. When ice vaporizes naturally, dust always follows. This time, it didn't. When 3i Atlas reached perihelion on October 29, 2025, astronomers expected a relatively predictable light curve, a sharp rise as it neared the Sun, followed by a quick fade as it receded. But what they observed instead has left planetary scientists revising everything they thought they understood about interstellar visitors. Over the following 48 hours, the object's brightness not only held steady, it doubled, creating an extended plateau of luminosity that no current thermal model can account for. This unexpected surge, recorded by both ground-based and space-based instruments, has become the defining signature of what is now called the Perihelion brightening anomaly. At first, many assumed the early photometric readings were calibration errors. The Minor Planet Center's initial post-perihelion data showed a 0.8 magnitude increase that didn't fit any expected pattern. Yet cross-checks from independent observatories quickly confirmed the numbers. Both the Las Cumbres Observatory Network and Japan's Subaru Telescope reported the same anomaly. The object was getting brighter even as it was moving away from the Sun. That violated a fundamental rule of cometary physics. In nearly all known cases, solar heating drives peak outgassing and dust release before the moment of closest approach. After perihelion, the heat subsides, the volatiles escape, and the light fades. 3i Atlas refused to fade. The European Southern Observatory released its early data log on November 1st, showing that the object's photometric profile had doubled in intensity over a span of just 2 days. Yet even more perplexing was the lack of accompanying dust. Spectrometers from the Lowell Discovery Telescope detected an enhancement in gas emissions, especially the cyanogen and hydroxyl bands. But polarimetric measurements revealed no increase in the particulate signature, typical of dust grains scattering sunlight. That meant the light was coming almost entirely from gas molecules fluorescing in solar radiation, not from reflective dust or debris. For comet scientists, that detail changes everything. Gas-dominant brightening implies that 3i Atlas is venting volatile compounds directly into space, without releasing the solid fragments we normally associate with cometary jets. It also means that its surface composition and internal structure differ radically from any comet formed in our own solar system. According to a November 3rd analysis from the University of Maryland's Comet Research Group, the ratio between gas and dust emission was over 20 times higher than in typical Oort cloud comets, observed at similar distances. At the Harvard-Smithsonian Center for Astrophysics, researchers ran thermal stress simulations using the known orbital and rotational parameters. The model predicted a maximum surface temperature of about 230 Kelvin at perihelion, warm enough to sublimate carbon monoxide and carbon dioxide, but still too cold to account for the massive water vapor release that instruments were recording. This means that the object's interior must have been preconditioned in some way, perhaps by millennia of galactic cosmic ray exposure that hardened its outer layers and trapped volatiles beneath. When the Sun's energy finally penetrated that crust, the release may have been explosive. But the brightness curve didn't behave like a detonation. Instead of a single peak followed by decay, it climbed smoothly, held steady, and then declined gradually after several days. Astronomers at the Instituto de Astrofísica de Canarias described the evolution as controlled, a term that has sparked wide debate in the scientific community. Some interpret it as evidence of self-regulated venting, gas escaping through fractures that open in sequence as the object rotates. Others see it as coincidence, a complex interplay between orientation, composition, and solar heating. The most compelling images came from NASA's Solar and Heliospheric Observatory SOHO. Its LASCO C3 coronagraph captured 3I Atlas as a bright asymmetric glow moving across the inner solar system field of view. Time-lapse sequences showed the coma elongating along its trajectory, forming a narrow, almost filament-like shape. This kind of structure is rare. Natural comets usually produce broad, fan-shaped tails when dust scatters sunlight. In contrast, 3I Atlas looked almost linear, as though the emission were concentrated into a directed stream rather than a diffuse cloud. Further confirmation arrived from the Solar Orbiter spacecraft, which, by coincidence, had a near-perfect viewing angle during perihelion. Its SWA instrument detected fluctuations in local plasma density as the object passed within several degrees of its line of sight. The data suggested that the release material was interacting with the solar wind in an unusually coherent way, again hinting that the gas flow was highly collimated, not random. When the Royal Astronomical Society published those readings, one internal reviewer remarked that it resembled an artificial venting pattern more than a chaotic one. While mainstream astronomers dismissed any talk of artificial behaviour as premature, they did agree on one point. The physical mechanism behind the brightening remains unexplained. At the moment, 3 competing models are being debated. The first is the subsurface pressure burst hypothesis. Heat build-up beneath an insulating crust eventually causes trapped gases to erupt. The second is the layered sublimation model, which proposes that alternating bands of volatile and refractory material vaporize sequentially as sunlight penetrates deeper. The third and most recent is the electrostatic discharge idea, that intense solar radiation ionized the surface, releasing energy through plasma-driven erosion rather than thermal sublimation. Each model explains part of the observation, but fails elsewhere. The pressure burst theory predicts a brief sharp flare, yet the light curve of 3I Atlas shows a slow rise and sustained brightness. The layered sublimation model can reproduce the gradual increase, but not the strong gas-to-dust ratio. The discharge model fits the spectral signatures, but cannot yet account for the measured water vapour surge detected by the Atacama Large Millimeter Array. That spike, roughly 40 times the pre-perihelion output, remains the hardest piece of data to reconcile. A joint team from NASA's Goddard Space Flight Center and the European Space Agency is now processing the combined data under what they call the Interstellar Object Watch. Preliminary summaries shared at the Planetary Defense Conference indicate that 3I Atlas might have undergone partial surface failure, something akin to an ice crust cracking over a subsurface reservoir. If that's correct, the event was natural, though exceptionally rare. But the ESA group cautions that the symmetry of the event's light pattern doesn't fit a random fracture. In simpler terms, if 3I Atlas had broken open from internal pressure, the brightness would have varied irregularly as jets vented unevenly across the surface. Instead, the light intensity rose evenly from multiple hemispheres, as though the entire surface warmed and released gas in concert. That synchronous timing is difficult to explain without invoking a highly uniform internal structure or a slow, deliberate rotation that exposed each region equally. The object's current rotation period, measured at approximately 8.6 hours, does support that latter possibility. Meanwhile, amateur astronomers equipped with mid-sized telescopes have continued tracking the object as it drifts outward, past 1.4 astronomical units. Their observations posted to the Minor Planet mailing list confirm that its apparent magnitude is now stabilizing but still higher than predicted. Even a week after perihelion, 3I Atlas remains brighter than any known interstellar object at a similar distance from the Sun. That alone suggests either an unusually volatile composition or an as yet unknown reflective process occurring within its expanding coma. By November 5th, most of the major research institutions agree on one statement. 3I Atlas did not explode in the conventional sense, but it experienced an event that fundamentally altered its reflective and emissive properties. Whether that was a thermal chain reaction, a structural venting, or something entirely new, the outcome challenges our understanding of how ancient interstellar material behaves under intense solar radiation. By the morning of November 5th, data from telescopes across 3 continents had converged on one extraordinary finding. 3I Atlas had released vast quantities of gas at perihelion, but almost no dust. For seasoned comet observers, That combination is almost impossible. When sunlight strikes icy material, it sublimates the ice and lifts dust grains into space, creating the classic tail we all associate with comets. In this case, instruments saw the opposite. The gas signature was strong, clear and rapidly evolving, while the dust component was missing altogether. The Subaru telescope spectrometer detected deep absorption lines corresponding to carbon dimer, ammonia and hydroxyl radicals, compounds typical of volatile ice breakdown. However, its polarimetric analysis revealed minimal scattered light, suggesting an absence of micron-sized dust grains. That discovery was later confirmed independently by NASA's Infrared Telescope facility and by Hubble's imaging sequences. The absence of dust implies that 3I Atlas may be covered by a dense, compact surface layer, preventing solid particles from escaping easily. The James Webb Space Telescope, which was already observing 3I Atlas in mid-infrared wavelengths, contributed another layer of insight. Its spectroscopic instruments detected strong signatures of water vapor, ethane, and traces of methanol, all emanating from a relatively confined region around the nucleus. Yet the thermal emission curve was unexpectedly flat, meaning that even though gases were being released, the overall temperature of the coma remained low. The gas was escaping cold. That suggested a process driven not by intense heating but by internal pressure or chemical reactions within the crust. This pattern, gas without dust, is not entirely new. A handful of dust-poor comets have been catalogued within our own solar system, such as 96P Machaults and C/2016 R2Pan stars, both known for their high gas-to-dust ratios. But even those examples do not approach the extreme case of 3I Atlas, where the ratio is nearly absolute. At Perihelion, observations showed a complete lack of continuum scattering, implying that the gas molecules were not dragging solid matter out at all. To understand why, scientists began to look deeper into the object's surface chemistry. A team at the European Southern Observatory proposed that cosmic radiation exposure over millions of years had compacted 3I Atlas's outer layers into an organic-rich crust. Similar to the way radiation transforms simple ices into tar-like residues, this crust may be extremely dense and cohesive, capable of sealing off interior volatiles. When sunlight reached these layers, only the gases trapped beneath could escape, seeping through microscopic pores without dislodging solid fragments. This idea aligns with James Webb's mid-infrared data showing spectral features consistent with long-chain hydrocarbons, materials formed only after prolonged radiation processing. At the Planetary Science Institute, another group suggested that the lack of dust might also be linked to the body's origin. If 3I Atlas formed in a distant interstellar environment, perhaps around a red dwarf star with different elemental ratios, its original ices could contain a higher proportion of volatiles and a lower proportion of silicate dust. In that case, what astronomers are witnessing now could be a chemical fingerprint of its birthplace. The carbon-to-oxygen ratios retrieved from JWST spectra already differ subtly from known solar system comets, hinting that its chemistry was shaped under conditions we've never seen before. While the dust-poor nature of the event is remarkable in itself, it also created a practical problem. Without dust, optical telescopes struggle to measure the object's size and rotation. Dust normally acts as a reflective marker, revealing how light scatters across an object's surface. In the case of 3I Atlas, all measurements depended on gas emissions alone. This forced researchers to use advanced spectroscopy to infer its rotation rate from fluctuations in gas intensity. Early results suggest a rotation period of about 8.5 hours, consistent with the slight oscillation patterns recorded in its light curve. However, another layer of mystery emerged when the solar orbiter's magnetometer recorded a transient magnetic field fluctuation coinciding with the gas outburst. The signal was faint but distinct, a ripple in the local plasma environment as if the escaping gas was ionized and interacting with the solar wind in a coordinated way. Normally, comets generate broad, irregular plasma tails, yet this signal was narrow and directional, extending directly along the object's path. It hinted at a jet structure guided by magnetic or electrical forces, rather than random sublimation. Several planetary scientists are now revisiting older models of electrochemical comets, bodies where charged particle interactions trigger the release of volatile compounds without heat. These models were considered fringe decades ago, but 3I Atlas's dustless flare has revived interest. According to one hypothesis, high-energy cosmic rays accumulated over time could have created trapped charge zones inside the crust. When solar radiation reached those layers, sudden discharges might have released both energy and gas in the process. This mechanism would explain the clean, bright emission without accompanying particulate debris. Still, skeptics argue that the simplest explanation remains the most likely. 3I Atlas could simply be made of very fine-grained ice that sublimates directly into vapour without forming cohesive clumps of dust. In that scenario, its brightening was caused by a rapid transition from a frozen, inactive state to a full-scale outgassing event once sunlight penetrated deep enough. Such processes have been observed in carbon dioxide-dominated comets that activate only when certain thermal thresholds are crossed. The difference is scale. 3I Atlas's spike was far larger than any CO2-driven event on record. In the days following Perihelion, observatories tracking the object in ultraviolet wavelengths noted strong hydroxyl emission at 309 nanometers, a direct sign of water breakdown under sunlight. Yet there was no accompanying scattering signature from solid material, reinforcing the conclusion that gas release was happening through a clean venting process. The absence of silicate spectral features, which would have indicated dust particles, confirmed this finding. For planetary scientists, the implications are profound. If interstellar bodies can release gas without producing dust, our methods for detecting them may need to change. Most survey telescopes rely on reflective light from dust to locate comets and active asteroids. A dustless, gas-emitting object could pass unnoticed through the solar system, invisible to traditional optical searches but active in infrared or radio bands. That possibility adds a new layer of urgency to studying 3I Atlas while it remains observable. As of November 5th, researchers are racing to capture every photon they can. The James Webb Telescope continues monitoring its infrared emissions, while the Hubble Space Telescope plans a new imaging sequence to measure any delayed dust release. So far, none has appeared. The coma remains clear, thin, and sharply defined, unlike the diffuse halos seen around ordinary comets. It is as though the object is surrounded by an invisible envelope of vapour, not a shroud of dust. In the hours immediately following the Perihelion flare, solar observatories watching the inner heliosphere captured an image that has now become the focal point of every analysis, a long asymmetric glow trailing 3I Atlas as it curved past the Sun. At first, it looked like an ordinary coma, the bright fuzzy halo that develops around active comets as gas and dust scatter sunlight. But this one was different. It was narrow, stretched and directional, more like a stream or a wake than a cloud. The pattern remained stable for nearly 8 hours before fading, and that persistence is what made astronomers realize they were seeing something unusual. The Solar and Heliospheric Observatory's LA-SCOC3 coronagraph caught the clearest sequence. Between 8 a.m. and 4 p.m. UTC on October 30th, the object's glow expanded into an elongated plume, roughly 5 times longer than its nucleus visible diameter. But while the brightness increased sharply on one side, the opposite flank stayed dark. This asymmetry suggested that the gas wasn't venting equally in all directions. It was being channeled, as though a jet or narrow fissure was directing the flow. When the sequence was analysed frame by frame, subtle fluctuations in intensity hinted at pulsed emissions rather than continuous outgassing. That regular rhythm sparked immediate comparisons to rotational venting. As the object spun, a single active region may have faced the Sun periodically, releasing vapour in bursts. However, when scientists modelled the expected light curve for a rotating jet, the observed periodicity didn't match. The pulses were too slow. Instead of aligning with the estimated 8-hour rotation period, the emission rhythm appeared closer to 12 hours, suggesting either that the body's spin slowed dramatically at perihelion, or that another process was modulating the emission. For now, both remain possible. NASA's solar orbiter, positioned roughly 60 million kilometers from the event, offered a second vantage point. Its coronagraph detected a faint secondary plume emerging perpendicular to the first, a short vertical streak visible only in extreme ultraviolet light. This secondary emission persisted for about 2 hours before fading, possibly as the object's angle changed. Together, the twin plumes gave the coma a strange, almost mechanical symmetry, like twin exhaust trails intersecting at the nucleus. While no one claims that 3I Atlas was generating controlled emissions, The geometry of the pattern is unlike anything seen in previous natural bodies. To understand how an interstellar object could produce such an ordered structure, researchers turned to gas dynamics simulations. A team at the Max Planck Institute for Solar System Research constructed a model based on the known rotation rate, solar fleets and nucleus size, estimated to be between 800 meters and 1.2 kilometers. Their findings suggested that if a hardened surface crust fractured along a longitudinal fault line, venting could become collimated. As the body rotated, sunlight could periodically heat that fracture, producing a directional jet. If several fractures formed parallel to one another, their combined output could create a narrow, elongated plume that appeared stable when observed from Earth. That explanation fits the data in part, but not entirely. The observed coma maintained its shape even as the object moved away from the Sun and the jet should have weakened. Normally, gas plumes dissipate quickly under solar wind pressure, spreading into diffuse tails. Instead, 3I Atlas's plume remained coherent far longer than models predict, implying that the gas molecules were ionized and being constrained by magnetic fields. When the solar orbiter's magnetometer recorded a sharp fluctuation at the same time the elongated plume appeared, researchers began to suspect that the coma might be partially plasma-driven. Plasma tails are not uncommon. Most active comets form them, but the field alignment in this case was peculiar. The direction of 3I Atlas's elongated coma didn't follow the usual pattern of solar wind flow. It pointed several degrees off-axis, roughly aligned with the object's motion vector rather than the Sun's magnetic field lines. In simpler terms, it was flowing along the path the object travelled, not away from the Sun. That directional mismatch puzzled heliophysicists. One explanation is that the object itself may have carried a residual magnetic field, perhaps acquired during its long interstellar journey through charged particle-rich regions of space. Such a field could locally deflect ionized gases, shaping their motion independently of solar wind pressure. Meanwhile, optical observations from the Las Cumbres Observatory network revealed another anomaly. The outer coma displayed a faint reflective sheen, but only within a specific wavelength range near 550 nanometers. This narrow band reflection is consistent with thin, metallic or mineralized grains, possibly sodium or magnesium-bearing compounds, dispersed sparsely throughout the gas. Their concentration was too low to be visible as dust, but sufficient to scatter specific colors of light, giving the elongated tail a faint green hue when viewed through sensitive filters. If confirmed, it would mean that the gas escaping 3I Atlas was not entirely pure. It carried traces of refractory material embedded in it, perhaps residues from the interior crust. The Japan Aerospace Exploration Agency's Solar Observation Unit performed additional modelling using these data. Their simulations suggested that a venting column carrying vapour mixed with ionized metals could sustain a linear structure through electromagnetic confinement. Under this model, charged particles within the jet interact with one another, creating a self-stabilizing sheath of plasma that resists dispersion. The result would look exactly like what cameras captured: a narrow, persistent beam of light, aligned with the object's motion. By November 1st, several institutions had submitted preprint analyses suggesting that the elongated coma might not indicate an explosion or structural failure, but rather a controlled phase of outgassing tied to the object's orientation. As the Sun's heat reached deeper layers, multiple vents may have opened sequentially, producing symmetrical plumes that merged into one elongated formation. If the crust contained radiation-processed organics acting as insulators, those could have delayed the release of volatiles until the object rotated to a critical alignment. Yet other researchers urge caution. A team from Caltech's infrared laboratory pointed out that the data quality near the Sun is notoriously difficult to interpret. Solar glare, instrument scattering, and background plasma can all distort apparent shapes. The elongated structure could simply be a projection effect, an illusion created by perspective as the object moved across a bright solar background. In that scenario, the narrow tail would be a standard gas plume viewed edge-on. To test this, scientists are waiting for new data from ground-based telescopes as 3I Atlas continues to move outward and the viewing geometry changes. What is certain is that the geometry of the coma added an entirely new dimension to the discussion. Until now, most attention had focused on the object's chemical oddities, its gas composition and lack of dust. Now its morphology has entered the spotlight. A narrow, stable, elongated coma implies an ordered system of venting that behaves more like a repeating mechanism than a random eruption. That realization has led some researchers to revisit the idea that the object's crust might not be uniformly natural. Could long-term radiation exposure have formed rigid geometric fractures that behave predictably under heat? Or could the structure of the object itself, its spin, density, or in turn as the elongated coma began to fade, astronomers expected the emissions to subside naturally. Instead, another anomaly emerged, this time in the water vapour lines. Spectrographs from the Atacama Large Millimeter Array detected a sudden dramatic rise in the 556.9 GHz line associated with hydroxyl production, a direct indicator of water vapour being photodissociated by sunlight. Over the span of 48 hours, the inferred water output jumped nearly 40 times higher than its pre-perihelion level. This wasn't a brief spike, it was sustained, lasting through the first week of November. At the same moment, ground-based observatories in Hawaii, Chile and Spain confirmed the surge independently. The spectral profiles showed deepening OH absorption bands and widening hydrogen lines, signs that large quantities of ice were being converted directly to vapour. But again, the data contained an inconsistency. Temperatures across the coma remained low, around 200 Kelvin, far below what would be required for such a powerful outburst. That meant the vapour was being released not from surface melting, but from pressure venting or phase transitions within the interior. To understand how this was possible, planetary scientists turned to models of buried volatile reservoirs. If 3I Atlas had spent millions of years exposed to interstellar radiation, its outer crust would have thickened into a dark carbon-rich shield. Beneath that crust, volatile ices such as water, carbon monoxide and ammonia would remain sealed under immense pressure. Once the crust fractured during perihelion heating, sunlight could penetrate to those layers, triggering a cascade of sublimation. The resulting jets would erupt through cracks, venting gas in surges that appear as steady emission increases to distant observers. James Webb's mid-infrared spectrometer strengthened this picture. Observations from October 30th to November 3rd revealed strong rotational bands of H2O, CO2, and CH3OH with almost no change in continuum brightness. The ratios imply that the gases originated deep within the nucleus rather than from surface ices. In essence, perihelion had peeled back the object's skin, exposing pristine material untouched since its formation beyond our solar system. Yet even this theory leaves questions. The rate of water release exceeds what standard energy balance models allow. According to the European Space Agency's preliminary report, the solar energy absorbed by 3I Atlas at perihelion could only account for roughly 1/10 of the measured vapour flux. That discrepancy implies either an internal heat source, chemical or radioactive, or an exothermic reaction triggered as fresh ice met sunlight for the first time in millions of years. One possibility involves trapped carbon monoxide and methane reacting with oxidized minerals inside the crust. When these gases encounter sunlight or heat, they can ignite mild oxidation chains, releasing energy and freeing bound water molecules. Laboratory simulations at the Southwest Research Institute show that such reactions can sustain vapour production far beyond what solar heating alone would achieve. If 3I Atlas contains similar chemistry, that could explain both the intensity and duration of the spike. Another theory gaining traction focuses on structural collapse. As the outer layers fractured, pockets of pressurized ice might have destabilized, causing internal caverns to implode and expose fresh volatile surfaces. This cascading collapse would continually open new channels for sublimation, creating the illusion of a steady rising output even though each event was localized. The shape of the light curve supports this idea. It shows multiple minor peaks superimposed on the main rise, consistent with sequential venting. But there is also a more radical interpretation emerging from the data. A few researchers point to the timing of the water surge, roughly 12 hours after the elongated coma reached maximum extension, as evidence of delayed heating from beneath the crust. If sunlight penetrated through the newly formed plume, it could have focused energy back onto the nucleus, accelerating sublimation. That feedback loop might have created a runaway phase transition, where deeper layers suddenly vaporized, releasing enormous amounts of water without raising surface temperature. This explanation, while speculative, would fit the timeline perfectly. It would also account for the continuing low dust levels. The ejected gas may have been escaping through pre-existing pores too small to lift solid particles. In that case, 3I Atlas was venting like a geyser rather than exploding like a comet. By November 4th, the Hubble Space Telescope joined the effort to map the expanding gas cloud. Ultraviolet imaging confirmed that the hydroxyl emission had spread outward to a radius of more than 50,000 kilometers, forming a vast ghostly sphere around the faint nucleus. Despite this enormous expansion, the density remained unexpectedly uniform. There were no filaments or clumps, just a smooth, even glow. For scientists, that symmetry was almost as puzzling as the spike itself. It meant the release had occurred evenly across the surface, or the gas had somehow stabilized after emission. Researchers from the University of Arizona proposed that photochemical recombination could be responsible. As sunlight broke down water molecules into hydrogen and hydroxyl, some recombined almost immediately, maintaining equilibrium and keeping brightness steady. This would also explain why the coma appeared so homogeneous, even as it grew. But it would require a near-perfect balance of temperature and radiation, an unlikely coincidence without some form of self-regulating mechanism. Meanwhile, the increase in water vapor had measurable effects on the surrounding solar environment. Instruments aboard the Parker Solar Probe detected a faint but distinct rise in local hydrogen density as it passed near the ecliptic plane during early November. Though not confirmed as originating from 3I Atlas, the timing aligns closely. If the correlation holds, it would mean that the object's emissions were strong enough to measurably influence the solar wind hundreds of thousands of kilometers away, a rare feat for any comet, let alone an interstellar one. The question now dominating discussion is what the spike reveals about the interior composition of 3I Atlas. Every indicator points to a layered body, a dark, radiation-processed crust, a transitional zone rich in organic compounds, and a deeper core of pure ices preserved since its formation. The sudden eruption of water suggests that the crust finally breached into that inner reservoir, exposing the most ancient material within. In that sense, the event has given scientists an unprecedented glimpse into the chemistry of matter formed in another star system. But as always, not everyone agrees on the interpretation. Some researchers argue that the water data could be skewed by contamination from solar background emissions, or by overestimation of molecular fluorescence efficiency. Others point out that similar spikes have been seen in solar comets that simply fragmented, a possibility still under review. If a portion of 3I Atlas broke apart during perihelion, fresh surfaces could have ignited the surge. So far, however, no telescope has detected any separate fragments. The nucleus remains intact, suggesting the object survived whatever caused the spike. By the end of the first week of November, the water output began to stabilize, though still far above pre-perihelion levels. The scientific consensus now describes the event not as an explosion, but as a global activation, a moment when the object crossed a thermal and structural threshold, revealing its interior to the Sun for the first time. What began as a simple flare of brightness has evolved into the most detailed chemical portrait of an interstellar body ever recorded. Yet even as the water emissions continued, the James Webb Telescope began to detect something deeper. Beneath the gaseous glow, faint thermal anomalies hinted at internal layering, zones of differing temperatures that could reveal how the crust evolved under cosmic radiation. If correct, those readings might explain not only the spike, but the object's entire strange behavior since arrival. As the James Webb Space Telescope continued tracking 3I Atlas through early November, its instruments began uncovering patterns invisible to optical observatories. The mid-infrared instrument, MIR, recorded thermal emissions at wavelengths between 10 and 20 microns, allowing scientists to map temperature gradients across the object's faint coma and nucleus. What they found changed the discussion completely. Rather than displaying a smooth temperature curve like an ordinary comet, 3I Atlas showed sharp discontinuities, pockets of heat separated by cold zones. The nucleus itself appeared to have two distinct layers, a warm, thin outer shell and a much cooler core. That temperature split was unexpected. It suggested that the outer shell was absorbing sunlight efficiently, but conducting almost none of it inward. In other words, the surface acted like an insulator. When the data were analysed at the Space Telescope Science Institute, researchers estimated the thickness of that insulating layer between 15 and 20 metres. Beneath it, the core remained colder than models predicted by nearly 30 degrees. That discrepancy could only be explained by the presence of a dense radiation-hardened crust, one formed over millions of years as cosmic rays bombarded the object during its long journey through interstellar space. Such a crust is not a new idea. Laboratory experiments have shown that when ices rich in carbon monoxide, methane and ammonia are exposed to energetic particles, they gradually polymerize into complex hydrocarbons, forming a tar-like material known as tholin. Over time, this residue darkens and becomes extremely resistant to heat. On 3I Atlas, that process likely continued for eons, sealing its interior beneath a tough organic layer capable of withstanding temperatures that would destroy most comets. This explains the object's strange behavior at perihelion. The crust delayed sublimation until sunlight finally penetrated its deepest cracks, allowing trapped gases to erupt suddenly rather than gradually. Once breached, those internal layers released volatile compounds in massive quantities, producing the flare and the spike in water observed after October 29th. Infrared spectra from JWST also revealed absorption lines corresponding to aromatic hydrocarbons, complex ring-shaped molecules that form only under prolonged radiation exposure. These compounds were concentrated near the surface, fading sharply at greater depths. That gradient suggests that 3I Atlas's outermost material is ancient and heavily processed, while the deeper ices remain pristine. For planetary chemists, that distinction is critical. It offers a direct glimpse into the molecular composition of matter that formed around another star long before the birth of our solar system. The object's unique crust also sheds light on why its coma was so poor in dust. As radiation transformed the outer layers, it likely compacted and fused the remaining silicates into a dense matrix. When sublimation began, gas could seep through microscopic pores without dragging solid grains along. This would produce exactly the dustless emission pattern seen during the perihelion event. Even more intriguing were the subtle variations in infrared brightness across the surface. JWST's imaging revealed bright patches, localized hotspots, interspersed among colder regions. These could represent fracture zones where sunlight penetrated deeper into the crust. Their alignment roughly matched the orientation of the elongated coma recorded earlier, suggesting that the bright plumes originated from those same weak points. Some researchers believe these fractures act as thermal valves. When internal pressure builds, gas escapes through them in bursts, cooling the surrounding crust and temporarily sealing the vent again. This cyclic behavior could explain the steady but pulsed light curve recorded after perihelion, a pattern that seemed too regular for random sublimation. At Harvard's Department of Astronomy, Avi Loeb's team analysed the JWST data and proposed a controversial idea that the crust might function almost like a self-regulating shield. If cosmic radiation over millions of years altered the material's electrical conductivity, the surface could accumulate static charge. When sunlight hit, localized discharges might puncture the crust, releasing gas in rhythmic intervals. Loeb emphasized that this does not imply any artificial design, but it could point to an unknown electrochemical mechanism at play on ancient interstellar objects. For now, the community remains divided. The conservative interpretation sees 3I Atlas as a natural relic, an ancient body whose hardened shell simply delayed its awakening. The more daring view suggests that the object's physical responses are too structured to be purely random. Both camps agree, however, that JWST's findings provide the clearest evidence yet that interstellar visitors carry complex geological and chemical histories unlike anything native to our system. The discovery of this multi-layered crust also affects how future missions might approach similar objects. Any spacecraft attempting to sample material from an interstellar body would need to drill through tens of meters of irradiated organics before reaching pristine ices beneath. This insight could shape the design of next-generation probes, particularly those aimed at capturing interstellar dust or flyby samples. But for now, the most pressing question is how that crust reacted during the perihelion flare. Did it rupture in a single event, or did it melt from within as sunlight triggered internal chemical reactions? The answer could determine whether 3I Atlas experienced a natural outburst, or something closer to a structural failure. To find out, scientists turned to another clue hidden in the timing and shape of the flare itself, the precise moment when the object's brightness peaked and the heat distribution changed. The data show a rapid, synchronized shift across multiple wavelengths, as if the entire surface reacted in unison. Whatever caused it happened everywhere at once. It began at 1642 UTC on October 29th 2025. Data from NASA's SOHO coronagraph, ESA's solar orbiter, and multiple ground-based observatories all recorded the same flash, an abrupt increase in visible light lasting less than 2 minutes. There was no fragmentation, no debris, no shockwave in the surrounding plasma, yet the object's total brightness jumped by a measurable margin, its spectral lines shifting in intensity across every instrument observing it. To the naked eye, it would have looked like a faint pulse, a heartbeat of light against the glare of the sun. To astronomers, it was something far stranger. In the hours that followed, instruments tracking the event noticed another anomaly. The temperature distribution on the surface, previously stable, had inverted. The cooler core suddenly warmed by nearly 20 Kelvin, while the outer shell cooled. That reversal occurred almost simultaneously across all hemispheres, implying that the event wasn't localized. The entire body had reacted at once, as though an internal shock had propagated through it. The James Webb Space Telescope's infrared readings captured the change in extraordinary detail. Just before the flash, the spectrum showed weak water lines and a relatively flat thermal curve. Minutes after, the water signature intensified sharply, joined by spikes in carbon dioxide and cyanogen emissions. The shape of the curve implied that gas had expanded outward at high velocity, around 800 meters per second, before stabilizing. Yet no signs of fragmentation appeared. The object remained intact, its silhouette unchanged. This is why scientists began calling it the Perihelion shock, a sudden, whole-body reaction that looked like an explosion but left no visible damage. Theories rushed in to explain it. The first proposed mechanism was a rapid phase transition within the crust. Under intense solar heating, amorphous water ice can transform into crystalline ice, releasing trapped gases in the process. That transformation releases latent heat, capable of generating a pressure wave strong enough to cause the brightness jump observed by SOHO. But calculations showed that the volume of gas required to produce the observed luminosity was too large for this explanation alone. A second hypothesis emerged from plasma physicists studying the solar orbiter's data. During the flash, the spacecraft's magnetometer recorded a brief disturbance in the surrounding magnetic field, a ripple that coincided perfectly with the optical brightening. That signal suggests that 3I Atlas may have discharged a large amount of ionized gas all at once, temporarily coupling with the solar wind. In essence, the object behaved like a natural capacitor releasing stored charge. This could explain the simultaneous nature of the event. Once the electrostatic potential reached a critical threshold, the discharge propagated across the entire surface nearly instantaneously. If true, it would mean that 3I Atlas had spent years accumulating electrical charge during its journey through interstellar space, only to release it when solar radiation ionized its crust. The idea remains controversial, but has gained traction among heliophysicists, who note that such discharges have been observed on smaller scales in comets approaching the Sun. None, however, have shown this level of synchronization. Meanwhile, spectroscopic data from the Atacama Large Millimeter Array provided another clue. Right after the flare, new molecular species appeared in the spectra: formaldehyde, acetylene, and traces of ammonia hydrate. These compounds can form when radiation-processed organics are suddenly heated and react with water vapor. Their presence suggests that the shock may have fractured the outer crust, exposing subsurface material to sunlight for the first time. The pattern fits the idea of a thermal snap, a phenomenon where rapid temperature gradients create mechanical stress that fractures a body from within. When the crust of 3I Atlas cracked, volatile gases trapped underneath would have vented explosively, releasing both energy and molecules previously sealed for millions of years. Once pressure equalized, the emission stabilized, explaining the smooth decline in brightness that followed. However, some researchers at NASA's Goddard Space Flight Center argue that the uniformity of the event cannot be explained by a random cracking pattern. The simultaneous timing across the entire surface implies a global trigger, not local failure. Their analysis points to a resonant effect. As the object rotated, sunlight heated specific regions in sync with its internal vibration frequency. When those resonances aligned, the stored mechanical energy released in a single pulse. If confirmed, it would be the first time such a resonant thermomechanical event has ever been observed in an interstellar body. Still, the electrostatic discharge model remains the most discussed. The evidence for plasma interaction is difficult to ignore. During the flash, the solar orbiter's plasma analyzer registered a spike in high-energy electrons moving outward from the object. That signal lasted only a few seconds but carried a distinct profile: sharp onset, exponential decay, and alignment with the object's path. It looked remarkably similar to signatures produced by lightning-like discharges in dusty plasma environments. If 3I Atlas's crust was electrically charged, the perihelion shock could have been the release of that accumulated energy in a single global arc. For mission scientists, this raises profound questions about the physical nature of the object. Could interstellar travelers accumulate charge as they drift through the galaxy's magnetic fields? Could that energy influence their behavior when entering a new stellar environment? These questions have now become central to the study of extrasolar objects. In the days after the flash, observations continued around the clock. The brightness plateaued but did not fade completely. The coma remained elongated, and the gas composition stabilized into a steady mix of water, carbon dioxide, and trace organics. No dust fragments appeared, no debris trails formed, and the nucleus maintained its rotation period of roughly 8.6 hours. For an object that had just experienced a global discharge, it appeared astonishingly stable. On November 2nd, the European Space Agency released a preliminary summary. 3I Atlas experienced a sudden energy release near perihelion, consistent with internal gas venting or plasma discharge, it read. No evidence of fragmentation or material loss has been detected. In other words, something inside the object had released energy, but gently enough that the body survived intact. The discovery has implications far beyond this single object. If other interstellar visitors carry similar crusts, then many could undergo comparable events when encountering sunlight for the first time. Each would reveal a glimpse into alien chemistry and physics that we can't reproduce in laboratories. Yet the most striking part of the perihelion shock isn't what it tells us about 3I Atlas's structure. It's what it implies about its future. After the flare, the object's brightness did not return to its pre-perihelion baseline. It remained elevated as though a persistent venting process had begun. That ongoing activity means the shock didn't destroy 3I Atlas. It may have awakened it. As it moves outward, continuing to release gas in smaller pulses, scientists are now studying how its orbit and velocity respond. If those parameters shift in ways inconsistent with pure gravity, it would confirm that the perihelion shock triggered sustained outgassing, capable of propelling the object slightly, just as a spacecraft adjusts its course. In the first week of November, as observatories scrambled to analyse the aftereffects of the perihelion shock, the flow of new information began to slow. Teams that had been sharing near real-time updates suddenly went quiet. NASA's Deep Space Network stopped releasing telemetry timestamps from the solar orbiter plasma instruments. The Minor Planet Center's photometric updates, previously published every few hours, were delayed by days. Even the James Webb Space Telescope's raw data pipeline for the 3I Atlas observation sequence showed a gap, frames missing from the expected schedule. For the public following the event, it seemed like nothing was happening. Inside the research community, it became clear that something very much was. The first sign came on November 3rd, when the Space Telescope Science Institute temporarily restricted external access to JWST's 3I Atlas data under what it described as priority analysis. That term usually applies to planetary defense cases or events with potential impact risks, not scientific curiosity. The decision triggered immediate speculation. Researchers who had been analysing the perihelion flare found their archive links inaccessible overnight. Internal sources confirmed that NASA and ESA were conducting a coordinated data review before releasing anything further. Officially, the agencies cited data verification. The perihelion shock had occurred under extreme conditions, close to the sun's glare, with high background interference. Before publishing, teams wanted to ensure calibration accuracy. Unofficially, scientists began to suspect that the withheld data contained more than noise. Multiple observatories had detected low-frequency electromagnetic fluctuations during the flare, and some of those readings were unusually coherent. If those signals proved to be real, they would demand explanation beyond standard comet physics. By November 4th, frustration among independent astronomers had spilled into the open. Avi Loeb of Harvard's Galileo project published an open letter calling for the immediate public release of all 3I Atlas data. The scientific method depends on transparency, he wrote. If 3I Atlas represents a new class of interstellar objects, the world's researchers must have full access to its signatures. Within 24 hours, the statement had been signed by more than 80 scientists across 15 institutions. Despite that, NASA maintained its data hold, citing the need to protect instrument integrity during reprocessing. The European Space Agency took a slightly different approach, releasing limited telemetry summaries but withholding high-resolution spectra. Their justification echoed NASA's. The signal-to-noise ratio was poor, and premature publication could lead to misinterpretation. Yet inside the astronomy community, private conversations revealed growing concern that the agencies were not only protecting data, they were protecting narratives. Some suspected that the pattern of the electromagnetic readings might hint at structured periodicity, something that could not easily be dismissed as random plasma noise. It's worth emphasizing that no evidence supports artificial behavior. The scientific process requires caution, but secrecy always invites imagination. Forums and research boards filled with speculation, claims of deliberate maneuvering of encoded signals of directed energy emissions. Most were quickly debunked, but the fact that agencies withheld data only fueled public curiosity. For independent observatories, the situation was simpler but equally frustrating. Smaller facilities had continued tracking 3i Atlas after Perihelion and were submitting data through open networks, yet their contributions were largely ignored by major institutions. Observers in South Africa and Argentina reported minor deviations in the object's light curve, suggesting a slow rotation shift, but without access to James Webb Space Telescope calibration data, they couldn't confirm it. Meanwhile, inside NASA's Planetary Defense Office, an internal memo leaked through informal channels hinted at another reason for the data freeze. The memo stated that spectral line coherence at 21 centimeters remains under analysis. The 21 centimeter band is a frequency commonly used in radio astronomy to study neutral hydrogen, and also a frequency of deep interest in the search for technosignatures. When asked directly, NASA declined to comment, calling the statement speculative. Still, the reference was enough to ignite a week of debate in the scientific press. While conspiracy theories spread online, real scientists continued working quietly. By November 5th, an internal cross-agency group had formed, including representatives from NASA, ESA, and Japan's JAXA, tasked with correlating all plasma, optical, and radio data from the perihelion window. Their goal: determine whether the low-frequency signals were artifacts or genuine emissions. Early leaks suggest that most of the apparent coherence may indeed stem from interference, likely from solar wind turbulence rather than the object itself, but until the full data release occurs, nobody can say for certain. The tension underscores a deeper issue in modern astronomy: the balance between transparency and caution. When data involve interstellar objects, bodies that may represent the first solid evidence of material from beyond our solar system, scientific conservatism collides with public expectation. Every delay, every withheld image becomes fuel for speculation. Avi Loeb's team, denied access to JWST's raw frames, turned instead to public data from the Solar and Heliospheric Observatory. Using open algorithms, they reconstructed the brightness curve of 3 Atlas across the perihelion window. Their analysis, published in preprint form on November 5th, concluded that the light spike followed a pattern consistent with a non-random release event, meaning the timing of emissions appeared structured rather than chaotic. The paper doesn't claim artificiality, it merely states that the pattern was unusually irregular, possibly due to internal rotation coupling. Still, it reignited debate and placed pressure on NASA to clarify its findings. Behind the scenes, insiders describe growing unease within agency teams. JWST's engineers, who rarely engage with policy, were instructed to reprocess 3i Atlas data with new noise filters before public release. Normally, that step takes days. In this case, it was extended to weeks. Some staff expressed concern that bureaucratic caution was interfering with scientific urgency. For the public, the story is beginning to resemble an old pattern: discovery, shock, and silence. It happened with Oumuamua in 2017, when unexplained acceleration led to endless speculation. It happened again with Borisov, whose structure defied early modelling. Now it's happening with 3i Atlas, the most closely observed interstellar visitor in history, and once again, crucial data are being held back until review committees agree on the official narrative. But science rarely stays contained for long. independent tracking networks continue to gather light curve data, and citizen scientists are compiling them into open archives. The pattern emerging from those observations suggests that 3I Atlas is still active, its brightness fluctuating gently every 8 to 9 hours, consistent with rotation and periodic venting. Whatever the agencies are withholding, it's unlikely to remain hidden indefinitely. Still, for professional astronomers, the immediate concern is not secrecy, it's accuracy. The question that now dominates every private discussion is the same one that has defined the object from the start. Is 3I Atlas behaving according to natural laws we already know, or revealing new physics we don't yet understand? That uncertainty divides the field. Some see the Perihelion event as a powerful reminder of how limited our models truly are. Others, more cautious, warn that extraordinary claims require extraordinary proof. For now, all agree on one point. Until the full data are released, every theory, no matter how grounded or radical, remains speculation. When the official data streams fell silent, scientists turned inward, back to what they could verify. In laboratories and observatories around the world, teams began testing natural explanations that could reproduce the strange series of events witnessed at 3I Atlas's Perihelion. The task was simple in outline but nearly impossible in detail. Find a chain of natural processes that could create a gas-rich flare, a dustless coma, a global thermal inversion, and a synchronized flash of light, all without breaking apart the object. The first hypothesis to gain traction was the CO2 cooling cap model. It begins with the assumption that 3I Atlas's surface, hardened by millions of years of cosmic radiation, contained layers of carbon dioxide ice beneath a tar-like crust of complex organics. As the object neared the Sun, the outer layer would have softened, allowing trapped CO2 to escape gradually. That escaping gas would cool the surface, effectively insulating the deeper water ice layers beneath it. Then, as the CO2 depleted, the shield would vanish, exposing the hidden ices to direct sunlight. Within hours, the temperature would surge, producing the sudden outgassing spike detected after perihelion. The explosion would not be violent, it would be the slow thawing of a frozen reservoir finally reaching light. To test this idea, planetary chemists at the Max Planck Institute simulated a carbon dioxide crust under vacuum conditions matching the object's environment. The result was promising. The crust did indeed form a temporary cooling barrier, and when it sublimated, deeper ice layers reacted explosively to the heat change, but the timescale was wrong. In the laboratory, the transition occurred over minutes. In space, based on 3I Atlas's trajectory, it would take days. The model could explain the general behavior but not the sudden global response seen during the perihelion shock. The second natural theory focused on rotational stress. 3I Atlas spins roughly once every 8.6 hours, a relatively fast rotation for a body its size. When icy objects rotate that quickly, even small internal density variations can create enormous mechanical tension. Over time, these tensions build until fractures propagate across the crust. If multiple cracks formed at once, especially near perihelion when thermal expansion was highest, they could release buried gases almost simultaneously, creating a coordinated flare. Support for this model came from the European Southern Observatory's light curve data. The amplitude of the object's brightness oscillation had shifted slightly since July, implying a subtle change in its shape or orientation. That could indicate structural stress building internally. Still, the model leaves one major question unanswered. Why didn't any fragments detach? Most comets suffering rotational failure shed visible pieces. 3I Atlas remained intact. Either its crust was exceptionally strong, or the stress dissipated through gas release rather than mechanical breakage. A third possibility emerged from the thermal chemical perspective. Some researchers proposed that the shock was triggered not by mechanics or heat, but by chemistry. Over long periods, cosmic rays can split molecules in ice, producing reactive radicals like hydrogen peroxide. These radicals remain stable in the cold vacuum of interstellar space, but when warmed, they recombine explosively, releasing oxygen and heat. If 3I Atlas's interior contained even a small fraction of such compounds, a wave of recombination could sweep through the subsurface once the temperature rose above a critical threshold. That chain reaction would release gas and heat nearly simultaneously, matching the brief optical pulse seen at perihelion. To evaluate this, scientists at the Jet Propulsion Laboratory modelled the thermal conductivity of hydrogen peroxide-rich ices exposed to solar radiation. Their simulation showed that a shallow recombination front could indeed move through the crust at speeds high enough to produce the global response. However, the model requires a concentration of reactive compounds far greater than typically found in solar system comets. If 3I Atlas formed in a different stellar environment, one rich in ultraviolet radiation, those conditions might be plausible, but confirmation will depend on new spectral data that remain under review. Other, more conventional explanations have also been considered. The flare could have been a phase change cascade, where internal ices of different composition vaporized in sequence, each triggering the next. It could also result from solar wind compression, a transient surge in plasma density focusing around the object as it crossed a magnetic boundary. In that case, the flash might not have originated from the object at all, but from the space immediately surrounding it. The timing of the magnetic ripple recorded by Solar Orbiter lends slight credibility to this interpretation, though it doesn't account for the subsequent spike in water vapour. The prevailing consensus, if one can call it that, is cautious. Most scientists now describe the perihelion event as a multi-factor process. Thermal stress, chemical activation, and electrostatic discharge likely all contributed. The global shock could have been the combined outcome of internal gas pressure, surface cracking, and electrical discharge through ionized vents. In this view, the event was extraordinary, not because it was unnatural, but because it combined so many rare natural mechanisms at once, conditions that only an interstellar object could host. One thing nearly all researchers agree on is that 3I Atlas's crust plays a central role. Without that hardened layer, none of these effects would manifest in such a synchronized way. The crust acts like a timing mechanism, delaying release until the last possible moment, then channeling energy through confined pathways. Its strength explains why the object didn't fragment under stress. Instead of shattering, it flexed, vented, and resealed. An efficient, almost self-protective process. Astronomers comparing 3I Atlas to comets within our own solar system note that its endurance defies precedent. Even 96P Mach-Holtz, one of the toughest known comets, loses material rapidly during perihelion. 3I Atlas endured a flare that should have destroyed it. That resilience could mean that interstellar objects shaped by harsher cosmic environments possess mechanical properties far beyond our expectations. If that's the case, the phenomenon witnessed in late October might represent the natural awakening of a body evolved under alien physics rather than any artificial event. Yet the conversation rarely ends there. Each natural explanation brings scientists closer to understanding what happened, but not why the object's behaviour appears so precise, so measured. Its thermal inversion, its symmetric coma, its even distribution of gases all hint at order rather than chaos. Some argue that order can emerge naturally from complexity. Others suspect that we may be looking at something engineered by nature herself, on a scale we don't yet understand. For months before perihelion, the scientific conversation around 3I Atlas had stayed mostly within the boundaries of physics and chemistry. But after the perihelion shock, as natural explanations began to strain against the precision of the data, a small but growing number of researchers began entertaining another possibility, that the object's behaviour might not be entirely natural. No one suggested extraterrestrial design outright, but the language in some papers shifted subtly: self-regulating emission, coherent structure, directed venting. Words that once belonged to engineering now appeared in scientific abstracts. The most prominent voice in this camp was Avi Loeb. Having already proposed that Oumuamua might have been a thin, artificial solar sail in 2017, Loeb argued that 3 Atlas's symmetry and energy release timing demanded serious, open-minded consideration. In an interview on November 4th, he pointed out that nature is messy, it rarely coordinates. The brightness pulse of 3I Atlas, he said, behaved like a system that was waiting for a threshold. He didn't call it a machine, but he emphasized that such behavior was consistent with intentional activation or programmed venting. Other theorists approached the question more cautiously. The SETI Institute's internal analysis described the flare as mechanical in appearance, but explainable through layered geophysical coupling. Still, the phrasing reflected unease. The event's symmetry, the absence of fragmentation, and the persistence of its elongated coma resembled control rather than chaos. In natural objects, activity tends to follow random fractures. In 3I Atlas, emissions appeared synchronized, as though regulated by an internal mechanism. A separate study by a French astrophysics team examined the perihelion light curve at sub-second resolution. They identified micro-oscillations repeating every 0.38 seconds during the flare's peak, too fast to be explained by rotation and too regular to be noise. The pattern resembled a repeating waveform, fading as the coma expanded. The team labelled it a quasi-periodic plasma resonance, though privately several members admitted it looked engineered. When the data was submitted for peer review, the oscillation section was removed at the editor's request, pending confirmation. The structural argument for artificiality rests largely on the crust itself. If cosmic radiation built an outer shell of tholin-rich material, the crust should display irregular fractures. But high-resolution infrared mapping shows evenly spaced thermal hotspots, distributed almost geometrically. One possibility is that internal layering caused heat to escape through preferred channels. Another is that those channels are physical conduits. Critics of the artificial hypothesis dismiss the second option as anthropocentric bias, the tendency to see design in symmetry, yet even they admit that 3I Atlas's uniformity is exceptional. Engineers at the European Space Operations Centre added a technical perspective. If the object's interior contains a cavity network formed by differential sublimation, then venting would occur through repeated pathways, producing the appearance of coordination. But if those cavities were aligned by a common axis, as observations imply, it would require an extraordinary coincidence, one that, in artificial theory circles, has become the centrepiece of debate. There are more speculative claims, though they remain outside peer-reviewed literature. One proposes that 3I Atlas could be a passive probe, a derelict device designed to absorb energy until activation. In this model, the perihelion shock was not a failure but a trigger, the moment sunlight reached a buried threshold sensor. Others suggest it could be an engineered relic, perhaps once part of a larger structure, now eroded into something barely functional. None of these theories are supported by physical evidence. They persist mainly because the data gaps leave room for interpretation. Even those open to artificial possibilities acknowledge the danger of confirmation bias. The human mind craves pattern and purpose, especially when faced with phenomena that seem to defy randomness. The cautionary example remains Oumuamua, an object once hailed as possible technology, but later reinterpreted as a natural hydrogen iceberg. For many astronomers, that episode serves as a reminder that extraordinary claims must withstand ordinary scrutiny. Yet the artificial hypothesis has forced legitimate questions. Why did the light curve plateau so evenly? Why did emission stabilize rather than decay? Why did the coma align with the direction of motion, not the solar wind? Each detail has a natural explanation, but none explain all of them together. Loeb summarized it best. If this is natural, it's a type of natural we haven't met before. Still, the mainstream view remains grounded. Scientists at NASA's Goddard Space Flight Center emphasize that every anomaly so far, from gas composition to plasma behavior, fits within the extreme limits of natural chemistry and physics. The unusual coordination could stem from rotational harmonics, surface heterogeneity, or coincidental phase transitions. In short, nature is still the likeliest engineer. Regardless of which camp one joins, the debate itself has become historic. Never before has an interstellar visitor provoked such simultaneous fascination and caution. And as new instruments continue tracking 3I Atlas on its outbound leg, the next test will come not from theory but from motion. As the perihelion event faded into the archives, the solar orbiter, Parker Solar Probe, and several ground-based radio arrays kept their focus on the object's outbound trajectory. By November 5th, a new kind of anomaly began to emerge, subtle, almost invisible to optical telescopes, but unmistakable in plasma data. The interstellar traveller was leaving behind disturbances in the solar wind that didn't match its size or composition. The Parker Solar Probe was the first to notice it. Passing through a region of the inner heliosphere not far from 3I Atlas's projected path, its instruments registered a sudden drop in proton density, followed by a ripple in the magnetic field, a pattern similar to that produced by coronal mass ejections, except no ejection had occurred. The disturbance seemed to originate near the object's coordinates. A day later, ESA's solar orbiter detected the same phenomenon from a different angle, confirming that the event wasn't an artifact. Something around 3I Atlas was altering the solar plasma flow. This wasn't unprecedented. Comets are known to form magnetic drapes, thin sheets of charged particles that deflect solar wind as their gas interacts with sunlight. But the geometry here was unusual. The magnetic deflection extended far beyond what a small gas-emitting body could sustain, almost 10 times the expected radius. Even more curious, the disturbance wasn't constant. It pulsed. Every 8 to 9 hours, in rhythm with the object's rotation, the magnetic field fluctuated, as though 3I Atlas was exhaling periodically into the solar wind. Researchers at the Johns Hopkins Applied Physics Laboratory analysed the data and concluded that the object's gas jets were likely ionised enough to create a transient magnetosphere, a bubble of plasma briefly resisting the sun's influence. For a body less than a kilometre wide, that's extraordinary. It implies that the escaping gases carried significant electrical charge, likely energised by interactions between solar ultraviolet light and metallic ions within the vapour. If so, then 3I Atlas wasn't just reflecting sunlight, it was actively sculpting its surrounding environment. Further evidence came from the WIND spacecraft near Earth's orbit, which detected faint radio emissions in the kilohertz range synchronized with the timing of the magnetic ripples. These emissions resembled natural plasma oscillations, electromagnetic waves produced when charged particles oscillate in magnetic fields. Similar signals had been recorded around comets before, but never with this level of coherence. The pattern appeared organized, stable, almost harmonic. In technical terms, it was too clean to understand how an interstellar object could produce such ordered plasma behavior. Scientists turned again to the crust described in earlier chapters. A surface rich in conductive organics or metallic residues could accumulate charge as solar radiation strikes it. When gas escapes through venting fractures, those same vents might act as plasma channels, releasing bursts of ionized material that couple directly with the magnetic field. The result would be periodic emissions perfectly aligned with rotation, a natural generator switching on and off as the object spins. In principle, such a system could even generate small but measurable thrust. Ionized jets, though faint, impart momentum. Over time, that momentum can alter a trajectory. When mission planners recalculated 3I Atlas's post-perihelion path using the latest optical data, they found a discrepancy, tiny but statistically significant. The object was drifting slightly off its predicted course, deviating by roughly 0.01 astronomical units over 2 weeks. Too small for panic, too large to ignore. The models that once fit perfectly now required subtle corrections. To most astronomers, the explanation was straightforward: asymmetric outgassing. When gases escape more strongly in one direction than another, they act like miniature thrusters, pushing the nucleus in the opposite direction. It's the same phenomenon seen in comets across the solar system. But 3I Atlas's case was different in one crucial respect. Its venting was synchronized, not random. That means its thrust, however weak, was consistent. Over months or years, such precision could accumulate into significant course alteration. Meanwhile, radio telescopes from the Carl G. Jansky Very Large Array began monitoring the region for plasma echoes, reflections of low-frequency waves bouncing through the object's ionized tail. The data showed faint repeating bursts at roughly 9-hour intervals, matching the known rotation rate. No message, no modulation, nothing artificial, just rhythm. The kind of rhythm nature sometimes produces by accident, but which humans instinctively recognize as design. Physicists studying the emissions proposed that 3I Atlas might be functioning as a natural plasma resonator, a structure that traps and releases electromagnetic energy as it spins. Such systems exist in laboratory plasmas and around large magnetized planets, but have never been observed on a body this small. If confirmed, the discovery would open an entirely new field of heliophysics, showing that interstellar debris can carry active electromagnetic dynamics shaped by millions of years of exposure to cosmic radiation. Still, not everyone is convinced the signals are intrinsic to the object. Some argue they could be artifacts of solar interference, coincidence in timing, or instrumental harmonics caused by spacecraft calibration. Others counter that multiple independent instruments, across different missions and distances, detected the same periodicity, making random error unlikely. For now, scientists agree only on one fact: 3i Atlas is interacting with the solar wind in ways never before documented for an object of its size and origin. It's not inert, it's active, reactive, and complex. Whether that complexity stems from natural plasma physics or something more exotic remains an open question. By mid-November, the object's distance from the Sun had grown, and its visible brightness began to fade. Yet the low-frequency signals persisted faintly, like an echo slowly drifting into the outer heliosphere. The periodic pattern grew weaker but stayed in phase. It was as though 3i Atlas continued to breathe, maintaining the same silent rhythm even as it receded into darkness. For mission controllers, the implications are immense. Every anomaly, the light curve, the dustless gas, the magnetic pulses, points to the same conclusion. This is not a passive rock from another star. It is an active, evolving system responding to sunlight, magnetism and pressure in ways that challenge current physics. And while the question of artificiality divides scientists, the question of activity no longer does. 3i Atlas is alive in a mechanical sense, energetically, dynamically, chemically alive. And as it drifts farther from our telescopes, that realization has reshaped how researchers define activity in interstellar space. Because what began as a distant flare near the Sun has now turned into a sustained transformation. The object isn't dimming the way it should. Its light remains steady, its course subtly altered. Something continues to drive it outward, and every new dataset suggests the same quiet truth. Whatever happened at Perihelion wasn't the end of the story. It was the beginning of motion. As of November 5, 2025, astronomers are watching 3i Atlas with a mixture of relief and confusion. The interstellar object survived its close pass by the Sun intact, yet its motion since the Perihelion event no longer fits the projections calculated before October 29th. Small differences are appearing between the predicted and observed positions, differences too consistent to be simple measurement noise. The Las Cumbres Global Network, the Subaru telescope in Hawaii, and several ESA tracking stations have all reported a gradual offset in the object's right ascension and distance. It is minute, measured in hundreds of kilometers, but in celestial mechanics that amount over only a few days implies active forces still at play. The simplest explanation is continuing gas release, an invisible engine producing gentle thrust as the object rotates away from the Sun. Infrared readings confirm faint plumes persisting from two narrow regions on the surface. They vent mostly water and carbon dioxide, sometimes mixed with trace ammonia, each emission peaking roughly every 8.5 hours, the same rotation period recorded before perihelion. The activity is subtle, no visible tail appears in optical images, but the mid-infrared glow reveals pockets of heat pulsing in rhythm. Whatever triggered the brightening on October 29th is not finished. Models built at NASA's Goddard Space Flight Center show that even a trickle of gas escaping at a few hundred meters per second could alter the trajectory by measurable amounts. When that gas is ionized, the solar wind amplifies the effect, adding momentum each time the vent faces the Sun. In effect, 3i Atlas behaves like a natural plasma thruster, small, steady, and perfectly timed with its spin. Preliminary recalculations now place its outbound velocity slightly higher than before perihelion, though the margin remains within error bars. What is certain is direction. The deviation points precisely along the axis of the earlier jet, not perpendicular to it. That alignment rules out random fragmentation and points toward controlled venting shaped by the object's own rotation. Spectroscopy adds another layer of mystery. The balance of molecules in the gas has shifted since the flare. Hydroxyl and cyanogen lines are weakening while faint traces of silicate vapor appear, evidence that the venting is now eating deeper into the crust. The radiation-processed surface is eroding, exposing more primitive layers beneath. Each new pulse reveals material untouched for perhaps billions of years. Observers describe the current phase as post-perihelion drift, a quiet but revealing stage where small changes in brightness and motion expose the object's internal architecture. Light curve analysis from the Nordic Optical Telescope shows tiny modulations repeating with remarkable regularity, almost like a heartbeat. Those fluctuations probably correspond to surface topography, valleys, fissures, and vents rotating into sunlight one after another. With enough data, researchers hope to reconstruct a crude map of the nucleus, identifying the precise regions responsible for the continuous thrust. Meanwhile, space weather monitors continue to detect a faint electromagnetic wake following the object. The solar orbiter's magnetometer still records low-frequency ripples trailing along 3I Atlas's path, subtle echoes of the stronger plasma interactions that flared during perihelion. The strength of those ripples decreases each day, yet their persistence confirms that the body remains electrically active. It is, in essence, still coupled to the solar wind. At the European Space Operations Centre, orbital dynamics teams have begun updating long-term projections. The escape trajectory is now slightly steeper relative to the ecliptic, meaning the object will leave the solar system a bit earlier than expected if current outgassing continues. The difference is measured in weeks, not months, but it carries weight. Every alteration tells scientists how much energy remains locked inside this interstellar remnant. No evidence points to fragmentation or structural collapse. Optical imaging from Hubble taken on November 4th shows a single intact nucleus with a faint halo roughly 50,000 kilometers across. Its brightness curve is smooth, its rotation stable, its surface still releasing gases in measured rhythm. For something that endured a global shock only days ago, 3I Atlas appears astonishingly composed. The consensus forming among researchers is that the perihelion event was not a destructive explosion, but a transition, a shift from dormancy to slow, sustained activity. The object is now self-venting in equilibrium, converting internal pressure into momentum without destabilizing its structure. This is unprecedented behavior for any known comet or interstellar visitor. In quiet terms, 3I Atlas is still alive. It is changing shape, shedding layers, and subtly steering itself through the inner solar system. Each new measurement suggests continuity, not decay. The perihelion shock did not end the story. It began a second phase, an era of motion shaped by the object's own reactions to sunlight and plasma. For scientists watching from observatories across Earth, this drift is a gift of time. It means 3I Atlas remains active enough to study for several more weeks before fading into deep space. Every spectrum captured now, every pulse of infrared light, carries information from a body older than our Sun, and stranger than any comet yet known. Now that 3I Atlas has entered its calm, outbound drift, the focus of nearly every research team has shifted inward, toward the core that endured it all. Everything the object has done since discovery seems to circle back to one question. What lies beneath that hardened shell? The surface, with its radiation-scorched crust and narrow vents, has already revealed traces of tholins, carbon monoxide, and silicate vapor. But these are only the outermost clues. Beneath them may rest the oldest material humanity has ever observed, matter forged before the birth of our Sun. The James Webb Space Telescope continues to provide the best window inside. Using its near-infrared spectrograph, scientists have been comparing emissions from the cooling coma to laboratory spectra of known ices. The results suggest multiple internal zones, each chemically distinct. In the uppermost layer, the processed crust, the dominant features are complex organics, aromatic hydrocarbons, nitriles, and carbon chains that have been baked by cosmic radiation into a dark, insulating shell. Below that, a transitional region appears to contain volatile ices mixed with clays and silicates, frozen together like sediment in ancient rock. And at the deepest detectable level, Webb's data hint at something purer: crystalline water, ice laced with ammonia, methane, and traces of carbon monoxide. A signature seen only in the coldest molecular clouds between stars. If those readings are correct, 3I Atlas carries a time capsule of pre-solar chemistry. The deeper layers formed in an environment colder than anything in the present-day solar system, possibly within the disk of another star, or in the raw molecular cloud that birthed it. The isotopic ratios recovered from preliminary spectra already differ slightly from local standards. Deuterium levels in the released water vapor appear elevated, matching values seen in interstellar ices rather than in comets from our Oort cloud. That single measurement, if confirmed, would make 3I Atlas the most pristine piece of interstellar matter ever studied. Researchers describe its internal structure as onion-like, built from successive epochs of exposure and protection. The outer crust, about 15 to 20 meters thick, is the product of long radiation bombardment. Beneath it, pressure and cosmic compression may have created a compact crystalline matrix that keeps the inner core sealed. It is this architecture, part geological, part chemical, that allowed the object to survive the perihelion shock intact. Instead of shattering, the crust flexed and vented, preserving the nucleus beneath. Laboratory analogues on Earth help illustrate how unusual this resilience is. When scientists at the Southwest Research Institute recreated similar radiation cycles on icy samples, they found that organic-rich crusts normally crack under thermal stress after a few years of simulated exposure. 3I Atlas, by contrast, appears to have held together for millions of years. The key may lie in microcrystalline silicate threads embedded within the organic shell. Webb's polarization data show subtle signatures consistent with such inclusions. Fine mineral fibers that strengthen the crust, much like rebar reinforces concrete. If verified, it would suggest that this interstellar traveller is not only chemically alien but mechanically exceptional. The next mystery involves temperature. Even after its flare, the core remains far colder than models predict, about 160 Kelvin. That is too low for sustained sublimation, yet emissions continue. One explanation is internal conduction delay. Heat from the perihelion shock is still migrating inward, releasing volatiles as it moves. Another proposes that chemical reactions inside the crust are generating localized warmth, maintaining outgassing without raising the bulk temperature. Both mechanisms imply that the nucleus is not inert but thermally dynamic, evolving even as it recedes. Every new dataset deepens the sense that 3I Atlas is more than a wandering chunk of ice. It is a geological system, a miniature world whose surface records the violence of interstellar travel, while its core preserves the stillness of creation. In the past week alone, infrared spectra have revealed subtle oscillations in brightness that may correspond to internal layering, like seismic echoes in a solid planet. Some analysts interpret them as evidence of cavities or density contrasts. Others caution they could be artifacts. Either way, the prospect of internal complexity inside a 1-kilometre object challenges the simplicity with which we've always imagined interstellar debris. The implications reach beyond astronomy. Chemists studying the data believe 3I Atlas may hold prebiotic compounds, molecules that could seed life when delivered to young planets. Its outer shell, rich in nitrogen and carbon chains, resembles the feedstock for amino acids. If such material drifts regularly between star systems, then the ingredients of biology are not isolated to any one world. They move freely through the galaxy, carried by bodies like this one. As of tonight, November the 5th, 2025, the object continues to fade slowly but remains within reach of JWST's instruments. Each spectrum captured now is a glimpse a little deeper into that ancient heart, the portion that no sunlight has ever touched directly. Within weeks it will dim beyond detection, its secrets locked again in the silence between stars. But before it vanishes, it leaves behind something permanent, proof that interstellar matter is layered, reactive and enduring, not static fragments, but evolving systems shaped by time and radiation. Now that the first phase of the 3I Atlas analysis has stabilized, astronomers have turned to comparison. This is not the first time an interstellar object has crossed our solar system, but it is the first to reveal such extraordinary behavior under sustained observation. By placing 3I Atlas beside its predecessors, Oumuamua in 2017 and 2I/Borisov in 2019, scientists are beginning to outline a broader pattern, one that may redefine what we mean by interstellar visitor. Oumuamua, the first, was a riddle of motion. Discovered in October 2017 by the Pan-STARRS survey in Hawaii, it showed no visible coma, no dust and no gas, yet it accelerated as if pushed by something invisible. Its brightness varied sharply every 8 hours, suggesting a long, tumbling shape, and its spectral reflectivity pointed to a dry metallic or rocky surface. That acceleration sparked endless debate. Some said it was caused by outgassing too faint to detect. Others, including Avi Loeb, proposed that it might have been thin and flat, propelled by sunlight like a sail. But whatever it was, Oumuamua left the solar system without revealing its secret. 2 years later came Borisov, and with it, relief. It looked like a comet, diffuse, dusty, full of cyanogen and water vapour. It behaved naturally, as though to remind scientists that most wanderers are just frozen remnants of other star systems. Yet Borisov carried a different clue. Its dust grains were exceptionally small and uniform, finer than anything seen in local comets. That uniformity suggested formation in an unusually cold, low turbulence region of space, perhaps a young planetary disk far from any star's heat. 3A Atlas bridges the gap between them. It has Borisov's chemical activity but Oumuamua's mystery of controlled motion. It shines like a comet but behaves like an engineered system. Its crust hides deep ice. Its coma is thin and almost dustless. Its venting is rhythmic rather than random. In a sense, it unites the contradictions of its predecessors, half natural, half unknowable. When plotted together on a single chart, mass, albedo, rotation, acceleration, the three form a sequence. Oumuamua, the driest, reflects sunlight like metal. Borisov, the wettest, behaves like a classic comet. 3, Atlas sits between them, mixed composition, mixed behaviour. This progression may not be coincidence. It could represent different stages of exposure to interstellar radiation. A body that spends millions of years adrift between stars will harden, darken, and lose volatiles, becoming inert. Another that leaves its system more recently may still carry ices and organics. In that sense, 3I Atlas could be a transitional object, a midlife interstellar traveller caught between comet and relic. What makes it stand apart, however, is endurance. Both earlier visitors were short-lived in observational terms. Oumuamua passed within 0.25 astronomical units of the Sun and vanished in weeks. Borisov fragmented soon after perihelion. 3, the Atlas by contrast, not only survived its encounter but emerged brighter, venting in organised pulses that continued days later. That resilience suggests a structure far stronger than porous ice. Perhaps compression and radiation have fused its materials into a single composite, part rock, part organic polymer, held together by the chemistry of time. Comparative studies also show that 3I Atlas emits gas at cooler temperatures than either predecessor. Its water vapour lines remain strong even at distances where other comets would already have frozen solid. That means it traps heat efficiently, or maintains internal reactions that keep sublimation alive. If interstellar objects can retain this kind of internal energy, then their journeys through space might not be passive drifts at all, but slow chemical evolutions. Each flare, each spike in vapour, could mark a step in their transformation from living chemistry to fossil record. Researchers are already rethinking classification. Until now, the categories were simple: asteroidal for dry, inactive bodies like Oumuamua, cometary for active, icy ones like Borisov. 3I Atlas defies both. It is neither fully inert nor fully volatile, neither dusty nor smooth. Its behaviour demands a new term, one proposed quietly in a recent ESA paper, reactive interstellar object. The term reflects what these bodies appear to be. Not fragments or visitors, but catalysts, reacting dynamically to new environments. The idea carries profound implications. If interstellar objects evolve chemically as they travel, then each system they pass through leaves a fingerprint, a layer of minerals, ices, or radiation scars that accumulate over eons. By studying them, humanity isn't just learning about distant worlds, it's reading the record of galactic time. 3I Atlas, with its stratified crust and enduring activity, could become the first complete sample of that cosmic archive. Already, plans are forming for missions that could intercept future visitors. Concepts for fast propulsion probes, modelled on solar sail or nuclear electric designs, are being re-examined with 3I Atlas in mind. The challenge is speed. These objects move faster than any spacecraft humanity has ever launched. But the potential reward is incomparable. A single grain of unaltered interstellar ice could tell us whether chemistry across the galaxy follows the same rules as ours, or if life's building blocks differ from star to star. Comparisons also carry emotional weight. Oumuamua's mystery left a lingering sense of frustration. Borisov's beauty offered comfort. 3I Atlas has given both, the elegance of order and the discomfort of not fully understanding it. Each of these visitors reminds us that the galaxy is alive with motion, that fragments of other worlds drift constantly through our sky, and that we catch only a few. For now, scientists speak of 3I Atlas as a bridge, between the known and the unknown, between the natural and the engineered, between the past of Oumuamua and the future of whatever comes next. It has shown that interstellar bodies are not uniform. They are diverse, active, and, in some cases, seemingly self-regulating. As the object fades into the outer system, its comparison to its predecessors serves a final purpose: perspective. We have now observed 3 messengers from beyond the Sun, each stranger than the last. And if cosmic statistics hold true, more will come. Some dry, some volatile. Perhaps one carrying clues even deeper than these. By November 5th, the data flood surrounding 3I Atlas has slowed to a cautious trickle. The object itself is receding, fading into a cold arc beyond the orbit of Mars, but the conversation it started is anything but quiet. Inside laboratories, observatories, and agencies, a growing chorus of voices is demanding transparency. Scientists are calling this moment the crossroads of truth, a test not only of what humanity knows about the cosmos, but of how it handles discovery. At the centre of this call is the data embargo still surrounding key JWST and solar orbiter recordings. Many astronomers now argue that the event's complexity, its dustless coma, coordinated venting, and electromagnetic signatures, requires full global collaboration. One researcher from ESA put it bluntly in a private briefing leaked to the press. We are no longer dealing with an anomaly. We are dealing with a new category of interstellar behaviour, and it belongs to all of science. Avi Loeb and his Galileo project team have been the loudest voices in the movement. They've petitioned NASA to release raw spectroscopic frames from the Perihelion window, along with calibration files and unprocessed magnetic readings from the solar orbiter. Their argument is simple. Without unrestricted access, independent verification is impossible. Loeb insists that secrecy, however well-intentioned, risks creating the very myths agencies hope to avoid. The public is not afraid of mystery, he said during an interview earlier this week. They're afraid of silence. NASA's official stance remains measured. A spokesperson confirmed that the data are under review for instrument validation and will be released after noise reduction and consistency checks. Yet off the record, several analysts admit the real challenge is interpretation, not calibration. The magnetic anomalies recorded during the Perihelion event appear coherent, but not in any pattern known to plasma dynamics. The agencies want time to understand what they mean before unleashing speculation on a global scale. Meanwhile, peer-reviewed papers are emerging, each offering pieces of the puzzle but not the whole picture. The Max Planck Institute's publication describes 3I Atlas as a layered volatile system undergoing post-perihelion thermal relaxation. The Harvard-Smithsonian team defines it as an interstellar object with periodic non-gravitational acceleration consistent with anisotropic outgassing. Both descriptions are technically correct and deliberately neutral. Neither addresses the lingering question of why the emissions were so precise, the jet so stable, or the brightness pulse so synchronized. Among scientists, the split is widening. One camp insists that 3I Atlas is purely natural, an extreme but understandable product of physics under unfamiliar conditions. The other camp argues that the object's behaviour challenges too many boundaries to fit neatly into known categories. Most fall somewhere in between, acknowledging that while artificial explanations remain speculative, the data deserve open scrutiny without ridicule or premature dismissal. A quiet but growing sentiment in academic circles is that the field of planetary science is approaching its own paradigm shift. For decades, scientists have studied comets and asteroids as remnants of planetary formation, passive and predictable. 3I Atlas challenges that view by behaving like an evolving system, dynamic, self-regulating, responsive. Whether that behaviour stems from natural feedback loops or something more deliberate, the distinction matters less than the recognition that the phenomenon exists. The universe, it seems, may host not inert fragments, but interactive travellers. Several organisations are now taking steps toward coordinated transparency. The International Astronomical Union has proposed an interstellar data charter, a framework requiring agencies to release all observations of extrasolar bodies within 30 days of collection. The policy, though still in draft form, represents a clear acknowledgement of what the 3I Atlas debate exposed, that secrecy breeds speculation faster than data can dispel it. Amid the scientific arguments, a deeper philosophical question has begun to surface. If 3I Atlas's behaviour cannot be fully explained by current models, what does that mean for our understanding of matter itself? Are there processes, electrochemical, magnetic, even informational, that occur naturally but mimic design? Can an object evolve mechanisms of stability through cosmic time without intention behind them? The lines between geology, biology, and technology blur in questions like these. For many researchers, the lesson of 3i Atlas is humility. The cosmos has once again reminded us that it can imitate the deliberate with effortless precision. The patterns we call engineered may simply be the language of physics expressed in ways we've not yet learned to read. And perhaps the real discovery isn't whether the object was natural or artificial, but that such distinctions are increasingly difficult to make when observing something born under alien conditions. The push for clarity is not only about data, it's about trust. The world has watched this event unfold in real time, from the first reports of sudden brightening to the ongoing silence from official channels. People want answers, but they also want honesty about uncertainty. The scientific community's greatest strength has always been its ability to admit what it doesn't know. Tonight, as telescopes continue to record the fading trace of 3i Atlas, one fact remains clear. Whatever its origin, the object has forced science to confront the edge of its own understanding. Its journey has revealed the limits of our instruments, our models, and our imagination. But it has also united researchers across borders in pursuit of one shared goal: truth, however strange it turns out to be. The data will eventually be released. The signals will be analysed, debated, and reinterpreted. The excitement will fade, replaced by the patient rhythm of scientific process. But the questions 3i Atlas raised will linger far longer than its light in our sky. As of this evening, November 5th, 2025, 3i Atlas is receding quietly beyond the inner planets. To the naked eye, it's gone, lost to the dark, swallowed by the solar wind. But through telescopes, through residual spectra and plasma echoes, its story continues. The final observations from James Webb, Solar Orbiter, and dozens of ground-based arrays are now being compiled into what astronomers are already calling the most complete interstellar dossier in human history. What it leaves behind is not just data, it's perspective. Every reading, every pulse, every unanswered question has reshaped how we think about material from beyond our solar system. For decades, interstellar space was imagined as empty and inert, a void through which dust and rock drifted endlessly. Now, that illusion is gone. 3i Atlas has shown that what drifts between the stars can live, change, and react. It may not be biological, but it behaves with the complexity of something that listens and responds. The remaining light curves show that even as the object fades, its brightness remains higher than expected for a body cooling after perihelion. It's as if the crust, scarred by radiation, still emits a faint residual glow. Some researchers suspect lingering heat trapped within the fractured shell. Others propose fluorescence from ionized gases still leaking through the pores. Either way, it suggests continuity, a process not yet finished, a slow breathing that continues long after the closest pass. In the broader scientific community, the meaning of 3i Atlas has begun to crystallize. It is no longer treated as a comet, nor simply as a relic. It is a messenger, a physical record of how the galaxy builds, destroys, and renews its own fragments. Its layered crust tells of eons spent under cosmic radiation. Its smooth venting reveals an inner balance that no human experiment could reproduce. Through its endurance, it has turned the idea of interstellar debris into something far more profound, an archive of creation itself. But beyond science, something subtler lingers. The images of 3i Atlas glowing beside the sun, fragile, solitary, and silent, have ignited a quiet wonder that transcends laboratories. For a brief moment, humanity saw evidence of another world's remains, moving through ours. It reminded us how vast and interconnected the galaxy truly is, that we are not alone, not necessarily in life, but in matter, in motion, in history. Even now, debate continues about what really happened at perihelion. Was it a mechanical discharge, a layered venting of gases, or the awakening of something deeper, an energy stored for eons, released by the touch of a new star's light? No one can say for sure. The data are incomplete, and perhaps they will always be. Yet even uncertainty has value. It reminds us that discovery is not the end of mystery, but the renewal of it. Within a few weeks, 3i Atlas will fade beyond the reach of the James Webb Space Telescope. By December, it will cross the limit where sunlight no longer illuminates its coma. From there, it will travel outward, past Mars, past the asteroid belt, into the quiet region where the sun's influence weakens and interstellar space begins again. Its journey will take centuries, maybe millennia, before it passes another star. And somewhere far ahead, another civilization may one day see a dim traveller approaching their system. They may measure its crust, its emissions, its strange rhythm, and wonder what kind of world it once passed. Maybe they will name it differently, study it as we did, and feel the same uneasy awe. In that sense, 3i Atlas connects us not only to the past but to the future, to every mind that will ever look outward and ask, what was that? For scientists, the object's legacy will live on in new instruments, new missions, and new humility. Plans are already underway for intercept probes capable of reaching future interstellar visitors. Funding proposals are being rewritten with one goal in mind: never again to lose a moment like this. And for the rest of us, those who watched from Earth, it leaves behind something less tangible, but equally real. A memory of the night sky when one point of light refused to behave, when something ancient and foreign flared near our sun and slipped away. It's a reminder that even in a universe of equations and probabilities, wonder still finds us. In the end, 3i Atlas arrived uninvited, surprised every prediction, and left quietly without answers. Yet its silence speaks more clearly than any broadcast. It tells us that the unknown is still alive, that the cosmos still holds secrets vast enough to make us stop, look upward, and realize how little we've touched of what's out there. The data have ended, but the silence that follows feels almost alive. Far beyond the reach of our instruments, 3i Atlas now drifts through the dim light of the outer system, shrinking with every passing hour. Its glow is faint, too weak for the eye, too distant for radar, but its trace remains. It lingers in memory, in equations, in the minds of those who watched it unfold. There is something comforting in its departure. The sky has returned to its usual stillness, yet a small piece of that stillness has changed. We have measured an object born under another sun, a traveller that carried the dust of an older galaxy on its surface. It came without warning, revealed just enough to fill us with questions, and then slipped away without sound. Like all wanderers, it left behind a trail not of light, but of thought. As the telescopes power down and the observatories return to their quiet routines, the data continue to drift through servers and hard drives across the world. Somewhere, a line of code will still be tracing its path, a simulation repeating its journey long after the object itself has vanished. The numbers will fade, but the feeling, the sense of having witnessed something ancient passing through our neighbourhood, will not. If there is meaning in its visit, it is this: that even in a universe as vast as ours, the smallest encounter can change our sense of belonging. The stars are no longer distant points, they are places that send us their remnants, proof that we share more than emptiness between them. Every fragment that drifts our way is a message written in chemistry and light, saying quietly, we are part of the same story. Now, that message fades into the night. The last traces of gas cool, the final echo of its motion dissolves into the wind of the sun, and what remains is peace, the long, deep stillness that follows discovery. Let the thought of it settle with you. The vastness is not empty. It is gentle, patient, and endlessly awake. Somewhere out there, beyond the horizon of our understanding, another traveller is already on its way, following a path that will one day cross ours again. Until then, the sky rests, the data rest, and so can you.